Good morning, everybody, and welcome to today's course micro event on smart cities and healthcare. We are very pleased to have two eminent speakers with us today, Dr. Ursula Eicker and Dr. Anaya-Arenas with us. There will be two presentations. The presentation one is Digital Twins to Support Decision-Making for Urban Decarbonization by Dr. Ursula Eicker, Canada Excellence Research Chair from Concordia University. And the second talk is by Dr. Anaya-Arenas from ESG UQAM, also a course council member. Her talk is entitled An Iterative Exact Algorithm over a Time-Expanded Network for the Transportation of Biomedical Samples. So without further delay, I will give the floor to Dr. Ursula Eicker, who is the Canada Excellence Research Chair in Smart, Sustainable, and Resilient Communities and Cities, and founder and director of the Next Generation Cities Institute at Concordia University in Montreal. She works on decarbonization strategies for cities using living labs and urban digital twins for scenario modeling, user engagement, and operational optimization. She has a team of about 50 graduate students and software developers, which are working on multiple eco-district projects in Canada and on urban modeling and data analytics platform tools for cities. She has published 8 books, 20 book contributions, and over 140 peer-reviewed papers and more than 340 conference papers. Thank you very much, Dr. Ursula Eicker, for accepting our invitation. I give the floor to you.
So maybe you need to mute your mic. Can you hear me on the Zoom?
Yes, we can.
Okay, good. So thank you very much for the invitation. Let me just see that my slides advance. Okay. Yeah. Just to give you a bit of background, in the Cities Institute here, we deal in a very holistic sense with all topics of urban sustainability, built in natural environments, mobility, cybersecurity, and also community outreach. So what I want to talk about today is mainly related to the buildings and transport sector, because those are the biggest energy and carbon emission consumers worldwide, actually. And if you, of course, it changes from city to city, but mostly it's sort of 1/3 transport related, 1/3 buildings, and the rest is sort of more industrial use. So if we talk about, still a bit of an echo, I think.
Yes, so I think you can continue as
usual. So you probably need to switch your speakers off, or I don't know. Anyway, so if you look at roadmaps towards zero emission, away from the screen and speak like just the slides. Yeah, but I'm fine like this. I think it's more, I mean, we can't have two speakers. There's just an echo of the voice. Yeah, but if you switch in your audio settings, if you reduce your speaker to 0, then there won't be any echo. Okay, so we need to look at renewables integration and then, of course, decarbonizing mobility and buildings. So I have quite a lot of slides, so I move a bit quickly through some of them, but you can ask questions and come back to any of those. So basically, if you look at buildings and transportation, in the building sector, if you talk about decarbonization, first of all, you need to reduce the demand. That's always the best strategy, and then electrify. And electrifying buildings means mainly going from gas to heat pumps. And this is an example on the left side. Those are actually the costs of the retrofit of the Empire State Building. Very interesting project, because they actually did a lot of changes to the envelope. They changed the windows. They put triple glazings. And they did it all on site. So they took the old windows out, they constructed on one floor a real factory of adding another window pane, putting it back on. And by all these measures, and also, changing lights, and so they managed to reduce the demand so much that the new chillers they put in and heat pumps were so much smaller that they saved a lot of money on the equipment size because they needed to replace the chillers. So that in the end, the project was financially viable and even positive. So it can be done even on sort of really historic old buildings. The problem is that both in Canada and the US figures are the same. Just now we're only at about 10, 12% of heat pumps. So here in Quebec, it's a bit different. Most residential units are heated electrically, but just resistance heaters. So it's not even a heat pump. So we still have a long way to go. And other sort of much colder climates, or even here with 5,000 degree days, like Finland, they're at 40%, or Norway, some of the northern European countries show that it can be done. Okay, move on, no. Okay, so in transport, what we are working on is mainly the sort of urban planning side. So how do you make cities more walkable, more compact, more amenities? This typical 15-minute city concept that you might have heard about, very popular in Paris. So that's one side. So that is not really technical. It's again reducing demand. I think that's one of the main messages. It's always a good idea to first of all bring down demand rather than just changing from gas cars to electric cars. That requires a lot of resources. So it's always a good idea to reduce demand, and then and increase active transit, so bikes, walking, and so on. And then the only thing we work on in the mobility sector is then how to electrify more shared vehicles. I mean, I show you some results from a charging station location planning tool for electric buses. And of course, there are car sharing models. And we looked also at bike sharing. So I come back to that later. So my team is basically trying to build these urban digital models to see how we can get to the zero emission scenarios. And so one thing is to model the scenarios, and the other thing is how do you get people excited about it, so and wanting to change something. So we have these web interfaces. I'll show you some examples of this. We built a full model of Montreal. But then we also have some people working on game engines and basically importing the same kind of data into a game engine where you can then have much more interactive scenarios and have people change things and see how do they like the space, or have them leave comments and give feedback on, for example, on a project here with ARTM on designing a new mobility hub in the Bonaventure area. So that's basically what we try to do. And of course, if you try to model an entire city, it's pretty complicated because you have a lot of domains, transport and buildings, but also all the others. I mean, livability, greenery, water management, food supply, and so on. So we basically try to connect all these different domains and then have some calculation engines in the middle, and then so the results of these engines deliver the results to web interfaces, gaming engines, apps, and so on. So I think the main thing is to really have a good software architecture so that many people, students, researchers can add. And I think that's one of my suggestions also for you. I mean, I know you're working, there's quite a few of you working on transportation. If you have interesting models, it's a real pity that everybody develops super nice models, but then you leave and it's lost. So we have a few software engineers who really try to integrate different tools mainly from grad students, so that we can expand more and more the functionalities. And I think for that to work, you need to have a really good structure of managing your data. So we basically said, okay, we want to run simulations. I mean, energy simulations, agent-based traffic simulations. And so we know exactly what these simulation tools need. And that data we structured nicely in a central data model, because you will never get the input data harmonized. Every city does it a different way. I mean, some have Excel files, some have databases. there will never be a standard. So you need to have some importers, but what you can standardize is the central data model, because from there on, once we've got the data in here, it's always going to be the same process. We always feed the simulation models and manage the results. And I think that was the idea from the beginning. And so we built then, that was actually a postdoc who started with that, to build a 3D city model of Montreal using only open data. So, and it's not just data visualization. This is actually an agent-based model for transportation. So the interface shows real data, but also modeling results. So, and we basically, he started to just see, he started to collect whatever data is publicly available. There's a very nice tree inventory of all the public trees. No backyard trees, but public trees are all in there. So you can make use of all this data in different layers. That's why we call it city layers, to then develop services. And I show you a bit what I mean by services. So I would say more than half of the team works on the building side here. So we did a lot of work on modeling scenarios for buildings. So you can now select any of these buildings. You get some information of usage, of the age of the building. And then we have a full process of generating attributes, because we know the volume, but we don't know exactly the construction. But you know more or less an office building from 1950 will have probably, 30% window to wall ratio and some concrete construction and some insulation and so on. So we put all these information to the different polygons of that building, and then we can run an energy simulation. So, okay, this is in French because we're in Montreal. Of course, it's also in English. You can then, once you've got the software structure well designed, you can then change languages and do what you need to do. So here, what we wanted to do is study renovation scenarios for the buildings, but now we've nearly finished also a layer on calculating CO2 emissions from traffic. Where I show you what that means. So you basically click on a building, and then you get automatically a sort of a PDF that you can download on the retrofit scenarios of that building. So how much, what the base case is, based on usage and year of construction, what would happen if you insulate the envelope, like walls, windows, roofs, what would happen if you swap the energy system from gas to HVAC to electric heat pumps and some photovoltaics and the combination. So that's what you get. And because we have a whole city model, now we developed a tool where you can then select a whole area, any kind of polygon on the map. And that gives you all the buildings and the use types in that area that you selected. And then again, you can do these retrofit scenarios, saying, okay, now as a function of age, for 1900 to after 2000, what are the range of carbon emissions per building? And of course, it varies from building to building. But you see already, as expected, the newer the buildings get, the lower the average emissions. So that is actually, and then we sort of said, okay, now we can again do some retrofit scenarios, and the individual points are now individual buildings. And then you can say maybe the oldest building, I do the envelope, the newer ones, maybe change the energy system or both, up to you. So these interfaces allow you to come up with scenarios. And then calculate, of course, cost, life cycle cost. The status quo, the good news is even if you do everything, you retrofit the envelope, you put a new heat pump system, you put some solar on the roof, the life cycle costs are lower for basically every building than what it is now. I think one of the problems is that today companies especially don't really look at life cycle costs. They want return of investment in a few years. They say, well, over 40 years, it pays back. No. So there's a lot of convincing to be done to change mentality more towards life cycle costing, because then it's worthwhile. So here you see that again, the status quo, all the buildings with their high energy consumption, and then you do these retrofit scenarios and you bring down the energy consumption, but also the costs are for most buildings lower than before. So that's what we can do now. Just a few words of what that means if you want to create a city model, because now we started with Montreal, but now we got a project with Quebec City. They want the same data. It's pretty useful for city planners they all have sort of climate action plans, but they have so far basically no way of calculating in detail how to do this. And so one of the main problems that it's the data here. NRCan, the National Resources Canada, they do provide geometry data for all cities in Canada, but you really need to spend some time to look at the data, because here in Montreal, we found some areas for some reason had these incredible high building heights, which were of course wrong. So there's a lot of data cleaning involved, and we have some people now who try to automate these processes. Because the same thing, basically the data is derived from LiDAR flights. So you fly over the city, you measure the height, but then basically the LiDAR is just a point cloud. So this here is considered like one single building, but of course it's a street, it's for sure multiple buildings. So you need to overlay that information with, for example, cadastre information or tax office data, where you see what are actually the individual buildings. So you cut it up in pieces, then you go back to the LiDAR data set and assign one height to every building. And you see it's, of course, a big difference. And the results for your energy models will be, of course, also very different. Okay, so that's what we do. So we have different data sources for usage, for geometry information, from different players. As I said, very hard to see. It would be nice if it would all be harmonized in every city. You could go to the same data source and just import the data. We are a long way off this. But so that's what we do. We import this data. We generate these IDF, means is basically the file type for Energy Plus, for an energy simulation tool, open source tool developed in the US by Department of Energy. And then we need to bring in all these sort of information about the occupancy of buildings, constructions, and so on. And if we can, we had some projects on accessing other data sets like building permits, renovation permits. They're also very unstructured data, so there's a lot of work needed to harmonize that. Anyway, that's the whole workflow. We enrich the city with all these attributes, and then we run the energy simulation. So maybe to finish off the building part, once you have the envelope, you can calculate the demand, but you also don't know what is actually inside. There's no data set that tells you this building has a gas heating system. Of course, companies like Hydro-Quebec or Énergir, they know, but they don't share the data. So, but we have statistics, and what we do, we know in a certain area of the city, 20%, for example, are gas heated. So what we did, we generated some energy models and then assigned to every building the heating system. And again, data modeling is pretty important because, as I said, once you know how to simulate anything, it could be a traffic flow or an energy system, you need to really structure the data well. For example, that an energy system consists of energy generation, you need to distribute it, you need to emit the heat in the building, maybe you have storage. So you really need to structure your data well. So we came up, this is basically our work to say what is a good classification of all these different components in an energy system. Then we bring in the data, feed the simulation model, and get the results. And I want to show you a bit. So typically you could do that building by building, but there's a lot of talk now in Montreal on using district energy systems, because in a way it makes life easier if you have one central generation unit and you just distribute basically the heat, maybe also the cold. Maybe there's a new technology coming on, then you don't need to go back to every single owner, which is a pain. In every building, basically, you have just a heat exchanger, and that's it. Whatever happens in your energy generation can change. It doesn't affect the consumers. So these networks are actually pretty interesting because you could also put some waste heat in. We have now a lot of data centers, lots of waste heat, and typically it just goes to the environment. Could be very nicely used to heat buildings. You could also put some solar or other energy sources into that district heating network. So we now spend some time of saying, okay, how can we automatically generate models for district energy? So same thing, we know already what the demand is, energy demand is. Then we know the street layout. So any pipes, as you well know, because the streets are dug up all the time, any pipe will go through a street. So we know where the streets are going, and then based on the demand of the different buildings and the street layout, we could then automatically generate this graph, which is basically a district heating network. So maybe I don't go into all the details here, but it's an optimization problem. You need to find basically the shortest path to connect buildings through the street network to minimize cost, of course. Yeah. So that's one thing. And the advantage is if you have lots of different buildings connected to one network, it's actually quite nice, because you might have heard that there's a lot of debate that Hydro-Quebec doesn't have enough peak power in winter. Because that's one of the main issues, that people heat their homes maybe at 6 o'clock in the morning, and then there's a huge peak and the network cannot carry it. If you have a commercial building and residential buildings connected to a heat network, then this peak doesn't occur at the same time. So that makes it really much easier to generate this. So the district peak demand is typically much lower than the sum of all the individuals' demands. That's actually one big reason of why district energy is interesting. And then, as I said, we try to minimize the piping lengths, and also the diameter, because you can imagine that the bigger the pipes, the more expensive. But on the other hand, you need to put all this heat through the pipes, so you need to minimize the pressure drop. So that's actually the optimization problem. So you need to construct the graph in the first place. Then you need to model the hydraulics. So there's basically water flowing through these pipes. And if you have water flowing through a pipe, you lose pressure, so you need pumping power. So the higher your pressure drop, the higher your pumping power. And you also want to minimize the heat losses, because if you have a central plant somewhere in the east of Montreal supplying buildings in the city center, you have already 20 kilometers of distance, you will lose heat. So that's a pretty complex use case. And so one PhD student has developed these models, and now we're using them for district development here in Lachine East. You might know it. It's the end of the Lachine Canal, where the Lachine Canal goes into the Lawrence River. It's a big district to be built. It's just now, it's a brownfield, basically nothing left, a few old industrial buildings. And there are private promoters wanting to build on that area. But because nobody has experience here with district energy, they're all very afraid how much it will cost. For them, it's much easier just to put baseboard heaters. Cost nothing, and they don't care about that it uses a lot of electricity. So basically what we're trying to do is we looked at the area, we have the urban master plan, and then we sort of calculate these energy scenarios. Sort of either this is the standard case, so everybody takes from the grid, everything is heated with electric boilers or baseboards, which is a waste, quite clearly a waste. And then we put some solar on the roofs, and then we modeled the entire district energy system for heating and for domestic hot water. So I just show you, and then I go to the transportation cases, because might be more interest. So what you do, here we have the 12 months of the year, and we basically model heating, cooling, domestic hot water, and the electric appliances. As usual, in winter, you have much higher heating demand. And because this is the base case, heating is very high because it's direct electric heating. So what happens now if we move to the solar scenario? So we put solar on the roof and facade. So on the roof, you get the most energy, and we put some on the facade where there's no shading. So you can generate part of that electricity demand by solar energy. And compared to the base case here, where we have quite a lot of heating, you reduce your heating because now we use heat pumps. So that already shows you how you can reduce your energy consumption in the area. And then this question of peak loads, you can reduce the current situation by some solar by about 12%. And then if you put the heat pumps in, you can reduce the peaks by 50%, which is good. I mean, that's really significant, because if you don't reduce the peaks, you would need to build new transformer stations. It's also costing money. The question is, it's always a different pocket. I mean, hydro pays for the transformers, but the real estate people pay for the heat pumps. So that's a challenge of what we need to do. Okay, now the district energy situation. So we studied different network configurations and temperature levels, and basically what the private sector wants to know, what is the best configuration, the minimum configuration. So we basically looked at using different sources. For example, here in that section, maybe a heat pump feeding from the canal water. Here's some industrial waste heat. So there's various options of heat sources. We also looked at geothermal energy, and then, of course, connecting everything with the district network. So this is the entire project. Everything is automated. So there's nobody sitting there drawing pipes by hand, what a typical engineering office would still do today, because they don't have these algorithms of automating the whole model. But now we had the problem, this district is not going to be built tomorrow. I mean, you start somewhere, maybe in 10 years, the next sector will develop. So to build an entire network, it will cost, I don't know, 80 to 100 million or so, is probably not possible. So the next thing we did, what happens if we develop, I mean, this area will develop in phases. So we did basically the first phase, looked again at the minimum network configuration and to minimize pressure losses. Also, we clustered the buildings into 5 different sectors with their own heat transfer station. And so that's basically the result of the optimization, how you would get to these scenarios that can reduce consumption and peak power by 50%. But you see already, we're talking here about costs of over $100 million and return savings, energy savings, because now we have less consumption of maybe 5 million. So you can already, simple payback, very, very long. So you really need to look more in detail of how can such a project become financially viable. And so it's pretty complicated because there are subsidy programs, but they're limited. There's subsidy programs for the piping systems, some for the central plant, which is the most expensive part. So we took some data from a build project here with lots of financial information. And then we basically did some financing scenarios. And I don't want to go into the details, it would take too much time. But basically, just one point here on the right, in the net present value sensitivity. So if you want to have a net present value above 0, which means the project would be financially viable, you would need about 16% subsidy for the project. And that actually does work because there's subsidy from diverse programs from Quebec. So that seems possible to get that amount of funding for the project, and then it would become financially viable. Okay, and just to finish this off, we also, what you often do, how close do we get to net zero, to a zero energy district? I mean, which basically means the red point is the current consumption level. Of course, if you start to bring in some solar, you generate some energy yourself, some renewable energy yourself. If you reduce the demand by heat pumps and the combination of solar, then you basically get to much lower electricity consumption and some quite significant self-generation. So you get basically pretty close to the zero energy balance. All right, okay, that was the building part. Now I want to spend a few minutes on the transportation scenario. So we have about, I would say, 10 grad students who work on mobility. And as I said, we're not transportation engineers. I'm not transportation engineer. I come from building science, but because transport has such a high emission part, it's absolutely essential to look at it. And because we also look at design and urban planning, as I said, that has an impact on how the transportation demand is. Show you a bit what we did on this electrification and charging station location planning and bike sharing demand predictions. And then, of course, in our city layers tool, we want to bring everything into a sort of spatially very disaggregated emission map. So that's basically what we're just working on. The same idea, you select an area. We have generated a synthetic population based on the origin destination matrices. And we know the mode choices in an area, and then the user can say, well, what happens if we change, if people take more public transit or buy more EVs or use more bicycles? What does it do to the emission demand? That's one use case we're currently working on. And as I said, we have this gaming tool. That's a project with ARTM. We really want to see how different design options of mobility situations influence the usage of public transit or active transit. So these are basically the use cases. We're pretty much finished with the CO2 emissions, the CO2 emission use case. But it's not live yet. And the citizen engagement part, this is a new mobility hub near Place Bonaventure that ARTM is planning. And so this really goes into the detail. They really want to know, what does the design of a bus shelter, what difference does it make? Do people like one option better than the other? Or what if you display if you put sort of big displays everywhere? So there's several points where users can actually change things and also leave comments. So that could become, we want to really try whether that could become a much better feedback tool for the Office of Public Consultation or the mobility agencies to comment on acceptability. I mean, Anjali, what we just talked on before, that would be nice to create some use cases for acceptability. We want to develop a proposal, another maybe possibility for collaboration for voltage, which is on electrification of society, and of course transportation will play a big role. So again, what we've done so far, we really want to expand these kind of tools of developing a kind of multi-stakeholder platform to plan electrification strategies. And so we're collaborating with a colleague from École Polytechnique who works on agent-based models. and colleagues from computer science here at Concordia, but there's of course possibilities for more people to come in these kind of projects. So in the end, we want to see, of course, what do the users want? How does the charging infrastructure need to change? What does it do to the electrical grid as it is? Because all this heat pumps, electric mobility will all add to the electric power demand. And then we need to see whether that's possible in the current grid situation. Okay, so this is all in the future. One of my PhD students who's been working on deep learning algorithms, and he did a quite interesting project on the Bixies, basically seeing how bike sharing works today, because of course you always want to have a situation where the number of check-ins and check-outs at a certain station in the city is pretty balanced, because otherwise you see all these lorries driving around and shifting Bixies from one place to the other, which is not very ecological, expensive, is not very good. And of course you could do some real-time monitoring, but again, you want to have some kind of prediction what happens in the next couple of hours to maybe give incentives to the users to say, maybe park your Bixie there, we give you $2 for much cheaper than running a lorry. So yeah, so that's basically was the goal of the study, to basically develop a model for short-term prediction of these bike sharing demands. And the interesting bit is it's a kind of spatio-temporal problem, because you have all these different stations, you know how they're used. That's what you saw on the first map. And you know there's of course a correlation of where people pick bikes up and where they drop them. So, and that develops over time. So there are various methods, and what Cheyenne looked at is this deep learning method for this spatial and temporal correlations between pickup and drop-off. So it's a graph-based approach. Again, he's nearly finished his thesis, so there are some papers published. I don't have time to go into the details, but it's basically a novel graph-based machine learning approach to predict these drop-offs. And of course, you need to check how your model performs. So the root mean square error and absolute error is better than the other methods that have typically been used so far. So it seems to be working well. And then you can really look at the ground truth and predicted pickups and drop-offs to verify that the model works well. So I think it's an interesting piece of work, making use of new deep learning methods. And now we need to see whether the Bixie company would be interested to use it. Okay, and the final use case is on electrification of buses. That's also a student quite far advanced in his PhD. Kayan worked on basically looking how what would change if you move from the current diesel buses to electric buses. Where would you place charging stations, and what would it mean to the timetable and scheduling? Because now, I mean, some of these electric buses have very limited range. I mean, you can get high range, very costly, but some have only, I don't know, 37 kilometers of range. So you would need to, they wouldn't even last a day. So you would need to also allocate time to the charging. And that, of course, has an impact on the entire sort of scheduling of the buses. So again, it's quite a complex optimization problem. I mean, you have predetermined routes, that makes it a bit easier, but you basically need to minimize the optimization problem is what is the minimum number of buses you would need to cover all the trips. So we don't look at new timetables. I mean, the timetables basically reflect the current demand. You could also probably work on how this demand will change over time, but this is something we take for as an input. But with the given demand and the given, you then optimize the number of buses to cover the trips and minimize the total cost and travel time of the deadhead trips from the depot to the beginning of the line or in between lines. So that's the goal. And I mean, the city, like many cities, have pledged to buy only electric buses in 2025. I mean, because they gave themselves this deadline, they went ahead and bought quite a lot of hybrid buses basically now to avoid having to buy pretty expensive buses. So we will be stuck with a hybrid situation for quite a while. And if you look at the prices, I mean, you see why that's an issue. I mean, it's basically 3 to 4 times as expensive than the conventional buses. And also these charging infrastructures are also expensive. So you really would want to minimize the number both of charging stations and the buses themselves. So that's what Kayan basically did. So again, you need a lot of input data, the routes, of course, the bus network, the timetable, and the type of fleet from different manufacturers. And then he developed mathematical optimization for the scheduling and the location of the charging station. And then in the end, you get the best schedule for buses and best locations of the chargers. So he worked on 2 different optimization model types, basically an arc-based and a path-based model. Again, I think he's in the call. You can ask him lots of questions for the details of this. I maybe just want to show you some results from that work. So, of course, because it's a very complex optimization problem, computational time is an issue. And basically, the branch and price algorithms performed much better. So the more, if you basically move to larger problems like, for example, here, 70 trips, 8 locations for fast chargers, and then 444 time slots, it's still solvable, whereas the CPLEX computational time just explodes. So, and that's basically the way the problem is solved. So we've got the routes here, and here we looked at 15 bus lines. We know the depots where these buses are parked overnight, and then we have 600 trips and the result of the optimization is then to cover all these lines at minimum cost, you would have 47 buses and 3 charging stations, and you would, from all the possible locations of charging stations, the algorithm gave these 3 required stations as the best result. Yeah, so that's what the model can do. It's basically, it works. It can be applied now to different situations in the city. And again, we need to see how, I mean, we already are Kayan is working with Giro, the software company who develops these optimization models, and we'll see how it can be used for real planning. Okay, that's it from my side. What I wanted to show is what these digital tools can do for, I would say, different stakeholders. So myself, I've worked a lot with the real estate sector and the city on the building sector. I mean, for these sort of transformation roadmaps to zero emission. But once you've got the models, you can also optimize, of course, the real-time energy management. And then we also looked at mobility topics around electrification and charging station location, sharing models just now for bikes would be also interesting to do for cars, the same thing. And to bring that all together, I think the key is to have a growing sort of open source software where people can connect to and bring in new models that you're developing in the different teams. Okay, so that's it. Thank you very much.
Okay. Thank you very much, Dr. Ursula Eicker, for your presentation. Now we will floor for questions. Are there questions from the audience for the speaker? So if not, then I will begin with, oh yeah, please.
Just out of curiosity, I think it's very interesting research. Have you had a chance to kind of put this in front of policymakers, like government and such, even like, specific funding pushing it? And what did they think? Are they kind of ready to implement with the tools that you've worked on? Or?
Yeah, maybe for the online, if you did hear, it was about whether these tools are used by policymakers, and of course, I mean, it takes some time to connect to all these stakeholders. I came 5 years ago, so by now, yes, we connected quite well to, I would say, diverse departments in the city, because the city is also pretty siloed. I mean, so that there is a horizontal office for the transition écologique. We have very close contacts to them. We do several studies for them on renewable energy, waste heat potential, geothermal potential in the metropolitan region. We do sort of roadmaps for the city's own buildings, because they have 1,200 buildings that they promise to go to zero emissions. So, but there's no, because I don't have the tools, I would say, they don't have this overview of a list of 1,200 projects, which ones to start with first. So we're talking about this, we have a project with them to develop these kind of roadmaps. But it's slow. I mean, you need to start with a few buildings, for them to trust what you're doing. So they give us data for a few buildings and we model them. And then we come up with the scenarios. And the same, we have a good connection with the Municipal Office of Social Housing. They also have hundreds, I think 800 buildings or so. Same thing, they all need retrofit strategies, because the cities typically have ambitious plans, but they all struggle with implementation. How do you do it when? So, I mean, because of my background from the buildings sector, I'm more connected with the building part. So that's a bit of a challenge, and that's, I think, why we need to collaborate. I mean, the connection to transportation. I mean, ARTM has been a partner of the Cities Institute for quite a while, and I don't think I showed you. No, I didn't show you the gaming part. Maybe I can let it run while we talk. So we talked with. I mean, this is again more buildings, but I think there are other tools more related to mobility. But you basically see the same models that I showed before, but now in a game engine. Basically, you can change stuff, and then people can zoom into street level, see how the changes look, and then comment and so on. And so ARTM is pretty interested in that, and also the Office of Public Consultation, because that's what they typically do. They want to show maybe a new development somewhere in the city, and then they want people to comment on it. And it's pretty difficult for people to even imagine how it looks like if you see it as a paper plan. So now we have quite a nice project with the Office of Public Consultation and the Regional Transport Authority on exactly this, sort of using gaming for citizen engagement. And but it takes time, because a lot of these connections depend on personal trust. They need to know who you are, what you're doing, and it's always good to have a real expert in the background, which I can nicely say for the building side. On transportation,
city official ordinance called question. Oh, it's very scary.
Sorry, not again, no. Anyway, yeah, so that's my answer. Yes, and there's also the provincial level. The Environment Ministry is currently intending to build a virtual park of all of Quebec. So we have a couple of projects with them on developing better models for the buildings. And Hydro-Quebec is very involved in this because they think about demand and demand reduction. And yeah, so we do what we can. I mean, I think to me it's all about impact. So I want external people to use it, but you need to have something to show them. That's why I mean, we started with the building use cases, but that's why I want the transportation emission use case, just to say, okay, you can go on the web, you can see it yourself, you can calculate some scenarios. You need to have something to show if you talk to get people interested. And
All right. So are there other questions? So I will ask one question is that in general, when we look at the cities, there are a lot of, things that are important, but we do not really like them because they create congestion in the city and there is more or less often construction works going on. So in smart cities, how are these things going to change ongoing construction activities, traffic congestion, let's say a software not working and our transit system is stopped, creation of a new transportation systems, will they be as we see in normal cities, or we have to do some design work to not have same level of activity as we have in the world?
yeah, I mean, I clearly think that we need to reduce demand, because even if we change now to electric vehicles, I mean, it won't solve congestion. If everybody does exactly the same as before, the congestion problem, I mean, the air quality will get better, fine, but it won't really solve congestion. And I think to me, it's in a way, it's a bit of an opinion, of course. I really think we need to move towards more mixed-use, compact neighborhoods with lots of amenities in the neighborhood, not just one. I mean, it doesn't mean everything should be downtown. This sort of polycentric concept where you have different centers where people more or less have everything they need in their neighborhood. I think that needs to come, and especially around transit stations. I mean, there's this big debate now in Montreal. I mean, what happens to all the new RAM stations? How will planning take place? And as you know, there's a lot of protest against it in the old residential neighborhoods. So I think that needs to be negotiated with the residents for each setting, what is really acceptable for them in terms of density. And it's a difficult question, but I think unless we reduce demand, it won't really bring the change needed. And I mean, some cities are going for it very strongly. Paris, I mean, the 15-minute city comes from Paris, basically. I mean, I'm in contact with Carlos Moreno, the 15-minute city guy at the Sorbonne. He really pushed that concept, and they implement it quite strongly. I mean, Montreal is going a bit in the same way with bike lanes, but it's still quite a long way off, and the same kind of protests. So in the end, the population needs to go with it. If you do it against the population, at some point you just won't get elected again. So I think it's a top-down problem. I mean, to be courageous for these kind of decisions, but at the same time you need to communicate more with the population and make them a bit more excited. Maybe that this more walkable neighborhood is actually nice. I think all the projects I've seen where it's been done, like in New York, Broadway, for example, it was super car ridden, and at some point they just closed it and put street furniture, and now people love it. And I think you just need to have some good examples to show that it works, and then hopefully acceptance comes. But yeah, it's a difficult, and especially here in Canada, I mean, the car culture is pretty strong. So it will be yeah, it's a long way to go.
Sure, yeah. Thank you very much. Great insights, Dr. Ursula Eicker. So now we will move to the second speaker of today's talk. We have Dr. Anaya-Arenas.
Yeah. Very well.
Sure. Thank you. Her presentation is entitled An Iterative Exact Algorithm over a Time Expanded Network for the Transportation of Biomedical Samples. Dr. Ana Maria is an industrial engineer with a PhD in administration science. Ana Maria is an associate professor in operations management at the Universite, the Quebec Montreal Business School. She is mainly concerned about the planning, design, and optimization of the logistic network and distribution decisions in humanitarian and healthcare logistics. Her latest work focuses in fairness in distribution, network design with time dependencies, as well as efficient modeling and resolution approaches for real-life distribution challenges in healthcare. So I will now pass on the talk to Dr. Ana Maria. Okay, thanks very much. So we are now setting up for second speaker. Just indeed, please take a break. Sure, and
Thank you. Maybe I need to talk.
okay, thank you. So we have 1 minute. In the meantime, I will introduce myself. My name is Anjali Avasthi, and I am currently working at Concordia University. I am also the president for Canadian Operations Research Society. I see many of us are students here, so if you need to reach me out for any question or queries, feel free. In the chat box, you can write a message, and I'm writing my email for the benefit of student chapter. If you need any assistance or help, feel free to drop a message. So Dr. Ana Maria is now online, and I will pass on to her. Thank you.
Not sure.
Now we can see it.
And I will turn, so September 2021, how are you doing? I don't know if you hear me well. My mic is up.
Yeah, perfect. We can hear you.
And I'm going to move a lot, so I will put you guys over here. Maybe you will not see me. I'm just going to stop my blurring and myself. And then, yes, thank you for coming and being here. Thank you so much, Anjali, for the invitation. I'm happy to join these efforts that we do to try to connect more and support usually. So my talk today will be probably much shorter than Dr. presented this, because I'm not going to share a full thing of doing, and also I am, of course, not in the same experience that she has, but it's more on the, I'm going to share one specific thing that is actually a project that is recently accepted for publication, So once you have like, but of course, long time in the making. So I'm sure you guys know how the deal is, and you work so long for something, and then you're kind of, if you have to like read the paper again, because you're definitely gonna read it. But this is actually one of another series of projects that I'm working on, and I think it's basically related to the transportation of biomedical samples, and I will talk to you a little bit more of the details of the motivation behind it, the case study that we've done, and I would like to maybe open the floor at the end for the discussion of how to link actually this first talk on cities and smart cities and sustainability to what healthcare initiative should be inside and maybe just chat a bit more. So I'm gonna go straight into the setting quite typical thing. I'm gonna start to explain a bit more why I can become interested in this process, which is actually a collaboration with the Ministry of Health and Social Services here in Quebec during my PhD, so a while back. And then the definition of the problem in general, I mean, this specific motivation or the specific contribution and the algorithm that we use to solve. So as I said, I started working on this during my PhD. Actually, I was approached, or my advisor were approached regarding the directors and one of the decision makers in the ministry that were looking to reorganize and centralize the process of the actually law 10. So in 20, it's going to be already more than 10 years, they started this process of re-centralizing, and now we're seeing like the next step of it, right? A full centralization of it. At the time, we started with over 200 different health centers or entities that were quite independent. What I wanted to do was create a cluster. So this is where the CUs and Cs that you know probably were born. Actually, you guys have maybe a pointer, so I don't have to be close to the computer here. Here. Always bring it over here.
Sure, no problem.
I will. But yeah, because what happened at the time is that we started to understand that makes, and I will open this discussion later on how centralization and decentralization should work. I think there is no one right side of everything. There is always a question of balance, but at the time what we start to realize is that we have a lot of entities that were quite, because they were independent, they become quite inefficient, and not only efficient, but only were not able to actually provide what they were supposed to. We're really very limited in terms of resources. We wanted to, well, the ministry wanted to start kind of a simplification of the patient's pathway and try to make the transitions more smooth. We will can also, I can share a personal anecdote for that I had this week on that. Very structured and support on the healthcare side, of course, all the budget constraints. So the idea of the Cs and CUs came in place. We have now 11 service clusters that were called CSUs, and then of course the main hospital and Institute of Immunology, Quebec, and they became like independent, and the structure became to be what we know. And part of that is that if we have this idea of centralizing, it makes sense. One part of the project was what we call OptiLab. So OptiLab was in charge of thinking about better, be more efficient and centralized all that is related to biomedical samples analysis. Because mainly this lab cluster that they wanted to create allowed them to have invest in like better capacity, so better machines, faster machines, better capacity to respond, and focus a little bit more or centralizing. And then the discussion of centralization and decentralization makes sense, right? Like, okay, do I really need to have a place to analyze samples in every CLC or local clinic in the province, in every small town? Probably not. But then you don't want to centralize everything. I mean, you don't want to centralize taking samples, because one can think of saying, oh no, let's build like super sample settings and then everyone will come here, but you want to have some sort of access to community. So then I'm able to go to my local clinic, not so far ago, and then actually this is working, but I want to go to the local clinic, take my sample, but then leave the management of the system, take care of how to analyze this work. So that's the idea behind, which I think makes sense. But of course, that requires a lot of investment, right? So investment in the technology, investment in the good information system, traceability of this entire thing, and also a very good distribution plan. Because it's not going to decentralize access to service. So still have local clinics,
at centralized analysis, I need to have some sort of backbone in it and then transportation from that. When I start working on this, and I'm not gonna say how many ago because it would really put me on the shape, but when I started working on this, the things were, we were far behind. And again, I'm from Colombia, and the president is in different places, and it's super fun that we have so many good things in Canada, and we do, but we still saw things that were quite in need of standardization in terms of the process. So at the time, drivers will take the sample, put it in their packets, and go deliver, like you call a taxi and you deliver like which we can imagine is not necessarily standard. So ministries start to organize all this at the time. Over 70% of the sites have independent contracts for transportation. 30 of them were just using taxis or cabs, and no guidelines or direction, no tracking control. And this is where we get started the process. So I'm really talking a while ago, but that was kind of the main motivation behind it. And when we get to it, in this became we call the biochemical sample transportation problem, because when we look at this, and this is a picture of Saguenay, Saint-Jean, and the type of glass that you have over the lake, and you think of this and you say, okay, this is kind of know how to do. This is routing. There's so many things on BRP. This is kind of know how to do, but they're not really just the BRP. There is a lot of specific things. And I will then share a little bit more detail of what the problem is in terms of management, but also what in terms of transportation and how we have to do it. So imagine that you have this one single SEC or sample collection center. So one single local clinic, elderly center, wherever it is that you take samples. And you can imagine that the process of sampling is continuous at that time. So every time in my graphic here is one sample that one patient that you draw blood from or one sample that you take. And then you do this for a period. So let's say that this one is over from 6 a.m. to 2 p.m. And then there is a question again. You want to decentralize access to service, but you want to centralize transportation, which means that you need to bring those samples to the lab. And the main key thing about this entire thing, and as you can imagine, samples are a very hard commodity to transport because of, I'm gonna let you guys help me out a little bit. What do you think is the challenge of the main thing? It's confidential, yes, so all the information system, I agree with you. But if I want to move this and think about my picture from Saguenay, like Saint-Jean, that I'm in one corner of the line and then I have to go to all the other next to it. Any thoughts? Any thoughts align? Lifespan. The lifespan of the samples. You're taking lifespan and you need to take it back inside of a specific lifespan. And then we can open the doors to the discussion of how long this should happen. And I know from experience of the project, doctors sit in a table and can discuss this for hours. But let's assume, and what the ministry did is that we said something. So they have a very specific lifespan, and it's actually quite short, much shorter than this is what in the case of a marine framework of perishable commodities, is like very high resolution. It's like in the extreme. Because what you can usually find is a few hours, 4 hours, 5 hours, from drawing from a patient until analysis. And then you have another part that I'm not gonna have, this is like, for me, still things that need to be explored, which is the time that happens between they arrive to the door of the lab and what they actually are analyzed. But let's assume that we can have a maximum time frame or maximum time lifespan of 5. Of course, not every sample is the same. Of course, not every sample has the same lifespan. So by sake of commonality, let's say that we all fix to this tightest one or the most urgent one or the sponsor. And if they are all the same, the most urgent one will be the first one that I collect. So the first patient will be the moment that I need to bring the samples back to that. So this means, if you bear with me here, this means that you go here, you draw the sample, then you see other patients, and you know that this sample, which became your most urgent one in your batch, you will need to do some batch, send this home, will be the most urgent one, and they need to arrive back at the latest over here, which is 6:15 plus 5, 11:50. At some point, you need to make a cut. When the latest that you could do will be just enough time to pick this up and get to the lab. But then you want to go straight and you have that one. Contingency. Let's assume here that you do a first pickup at 8:30. So in that case, you pick up everything that you collected, everything that was wrong from 6:15 to 8:30, and then you can make this pickup, you can visit the center and go visit someone else. It means make a route, and this route will have up to 245 hours to go back to the lab and make sure that all these samples are still live. But as you can imagine, what we're seeing here is a strong interdependency in the decisions, because if I decide to visit it quickly, let's say I'm gonna go right away to the center, I can visit it to the 30, and what I'm doing already is fixing the next time that I need to come. So I know that this next sample will be the further one, and this needs to come back to the lab before this time. So at some point I have to visit it, let's say here, and I'm gonna have then bring this, I'm gonna have a route time of 2 hours in this case. And then, so all these decisions are even connected. And not only that, the pickup decisions and the routing decisions are even connected. So this is the problem in reality. What it creates is what we call an operation and schedule synchronization. And according to Suarez, or again, Ursula Suarez and our team, did a very nice review, I think, on the problems and synchronizations. And this classified very well into those type of interdependencies and synchronization issues. How it has been usually dealt with is through timing. So actually, problem settings are usually included, but I will get to that later. Just to give you another view here, this is the same example, but realize that not only these decisions are interconnected or synchronized, but there is an impact on the actual number of visits that you do. What I mean by that is exactly the same as you see in my A side and my B side, so top and down. This is the same FCC, the same samples with the same lifespan, but here I'm able to visit with only 2 pickups. I will, of course, what that costs me is that my visit instead of 8:30 is gonna be at 10. So I pick up many, I pick a larger batch, but I have only 1 hour to go to the lab, so shorter routing time. So this is the kind of complicated problem, and what I show you once for one SCC, but what you have, of course, a network of SCCs. So different centers with different communities, you have different pickups required, you have a fixed lab. You will probably visit an SCC more than once in a day, as you saw. So they become very highly interdependent. And then the question of the fixed number of pickups that you will do became also a challenge, and this is actually what we want to explore in this case. And the lifespan of the samples make a time constraint not only in the visit of the center, but also in the routing decisions and how long you can actually drive. Other problems we have solved before, so in general, we have time restriction like this one. Well, we need to make decisions at the point. So the first approach that we actually do is saying, I will fix a maximum time and I will try to control this with, let's say, time windows. And this is actually our first approach. So we have one paper that explains they did this problem as a VRP with multiple time windows, independent time windows. So we have to do like time decomposition on our end. The next thing that we could do, and we actually do this with the ministry, was guarantee what we call a service level. So you told me how many times I will visit. I will not visit you the time window that you provided. I will respect some sort of maximum time between visits, giving some visit consistency. Or I will go into something, and this is also recently published. I will solve this, guarantee this maximum time, and I will maybe try to tackle the complexity of the problem in a working horizon kind of heuristic. And what we propose here now, because until now, all these problems, and it has been usually dealing with the literature, not only me, of course, and I published this, there's a few papers that have this quite specific problem too. They're usually defined as a classical R formulation VRP with multiple and interdependent pickups. But we can start thinking of things that might be hard this way. First, as the example that we just saw, the idea of having a priori aggregation of making a decision itself, how many pickups should I do? Where should I batch? How many batch should I put together? Because can of course lead to suboptimal solutions in the broader sense. Our calculation of pickups might be wrong. So actually, one of the first works that were related to this were done by the team in Austria, Professor Werner and their team. And they actually proved in a simple heuristic with some other case like that, with post-experimental analysis, they proved that in some cases, doing more pickups than the minimum is actually better for the plan because it implies to get all these people together. So what we're looking here is a new approach and it actually solved it in a stacked way. Because this is another main challenge of this language. So our lower bound is very, very bad. So those correlations become quite hard to solve, especially when you add the complexity of having interdependency and synchronization. So what we did is to propose a different approach. So a different approach. We said I will not model this problem as a BRP, but as a time expanding network. So I will multiply my network and of course the physical nodes will be multiplied by time periods and time station in a time space network. And the beauty of the top of that was that we were able to then deal with the synchronization and the dynamicity of the problem in a stacked way. And also provide more or better or high level of detail to manage. So instead of having a tool, when we take your work, how many pickups you actually need, let's see if we can actually do something that's better. And then test different regularities and decision because, and this was, you saw it in the beginning and I shouldn't have said it, but this of course is a work that I've done with a collaborator. So this is actually one of the first projects that my PhD students started working on, Daniel Campo. And it's a collaboration with Claudio Concordia, which is one of your own here in Concordia now. And when we was talking about this, I was like, this cannot be better. Like you're multiplying the network, this is too much. And I have to say that he was right. So we actually proved that he was good at, and I will share some results here. But what we are able to do here, and what we actually want is to kind of have different versions of granularity and test, because what you can imagine is that, of course, this network will become instrumental. And that part was right. Everyone knows it, right? Multiplying this will be quite hard. It can be comparative. What do we know? I'm going very quickly about it. Going very quickly about this, but you can look at the paper. All these have a very extensive literature review section of it because the problem is so particular that it has a lot of related problems. So you can think that it's kind of related to all the dispersibility operations. Dialogue, right? Maybe a lot of synchronization, inventory routing problems. So when you're dealing with this type of things, usually you send this and you're saying, this is a BRB. So you have to like have all these sections in your sections. I think the closest one in terms of characteristics are so a few contributions in the field of synchronization. Indeed, Michael Ronzovin, Universite Laval now, was provided a nice test bed that was used and been solved. There is quite a few papers that have worked in something a little bit less restrictive, so not exactly the same, but kind of similar. With all that is on healthcare. So you have all these type of settings that they use. And of course, you have the large also getting a little bit larger now side of the literature that works in the the method that we use to solve, which is inspired from dynamic discretization. What we did. So the key here is that again, and you can take some time later to see like the model of this problem. Model of this problem as a BRP can let you see to a program of 10 plus constraints. A lot of binary variables, and now we're able to have something quite compact. So this time expanded algorithm will basically have these are variables. So how many vehicles travel from one part to the other in our extended network? How many flow variables we need quantities itself? So each sample will be represented in the other. And you basically have a certain design from here. You want to make sure that you can respect the number of vehicles, that no vehicle stays in no land, that all your flow, like your regions and destinations are met, and an example is that, intermediate. First thing that we tried is what is Simplex able to do. So we saw this here. We set this to Simplex, as you can imagine, quickly becomes quite intractable, especially depending on the regularity of your time frame. We tested, as we're dealing with daily transportation plans inside a single region, we're testing it with regularities of 1 minute up to less than a minimum 1 minute, 5 minutes, 15 minutes. But that can be quite large. So we have a small pre-processing phase. I will not go into details, but basically, even when you send this to Simplex, you can set a network that is already kind of smart in the sense that you reduce nodes that are not feasible, and you reduce parts that are not feasible, which means that you can actually not connect them. But it still was very hard to solve, so this is why we went to an algorithm. As I said, this is inspired from the dynamic discretization algorithm, which generally has 4 phases. So this is kind of what I'm going to explain now. The first part is that you need to define a partial network or a lower bound computing model that will give you usually it's a reduction network, so it's a faster, hopefully a faster problem, and it's able to give you a solution fast, but not necessarily feasible for the real problem. But they give you a lower bound solution. This lower bound solution then sacrifices. If your solution is feasible at the end for the real problem, you need it. If not, which is usually the case, you need to think about how to repair. And you need to check the things. So in that, there are 2 things that can be done actually. Well, the first basic one is to actually share, and this is based on Bolen and Sappelsberg's work on like PDD. They have quite specific ways of reducing the length of the arc and the background attacks, so you add more asks, you have the real feasible time, and etc. And grouping power, which I will go into detail later. So that's one thing. You add more arcs, so you can have actually partial overbound and remove this and split it in 5. Second step is to say about the groupings, and I will do that. But then we have test feasibilities, and for that we have an heuristic that is able to give us a better, like try to provide a solution and see if this will give us an upper bound. We have another heuristic that gives us will seek to provide a physical solution with the outbound lower bound border that we found later on, and feasibility tests with a model. And then what you have is that you use this information to refine your network, define new groups, new nodes, and define and solve this. So what is our lower bound model? 2 things here. The first one, as you can imagine, what we wanted to do here is to give managers flexibility and to have higher level of detail. But that of course means that you can have quite a lot of commodities. So if you come back to my first image, in which we have a point or a sample that is collected in 15 minutes, in an hour you can have a lot of cakes and commodities in your network, and your model here, just to remind you that my flow variables here are per commodity too. So what happened is that we introduced what we call a commodity grouping, which is trying to find what will be a good cluster of commodities to reduce the time. The group feasibility is verified and separated if necessary. So we start with the first one, we'll group into just one commodity per SSC. But of course, this is not necessarily feasible. So you make sure that you were able to provide and deliver the commodity inside the time frame, if necessary, or deliver before perish, or if it can before they are all generated. So you create as many initial groups as possible, and with it you start your lower bound. And of course, then you have partially expanded network, so you look at all the nodes of LDRs as well. But what will happen with that is that if you solve it, you can quickly find solutions in your lower bound method that is kind of like this. You can have a trouble that starts in the lab, go to an SEC, and then go back in time with a trouble time of -4. So they have zero solution, and then things doesn't work. This iteration, a new model is created with the realization of this problem. We validate the grouping, the current grouping in the lower bound, if it is feasible, and if we have arcs extension that needs to be performed. If we have, if it is feasible, tackle again, but if not, we go to the second stage. And the second stage, we'll try to create things for two things. First, we test feasibility using the lower bound solution, so the exact definition of routes that the lower bound model gives us, and solve this LP model with the real groups and real-time restrictions. So the number of pickups that comes from the solution, the routes, so the arcs or the visits that are defined, we pass it here. This is an extension or a modification adaptation of one of the VRP models that we provide before. And of course, as an SLP, that's a super fast result, so we're able to check. So what we want with this is try to see if the solution is actually does make sense, but we need to find better time. And this model will let us. If we do, great, we found a feasible solution from the lower bound, so we are in that. If not, we pass to the next step, which is actually creating a new upper. For the upper bound, there are two things, and I'm going a little bit faster with it because I don't want to get into detail and have more time for discussions. But there are two ways of creating an upper bound. We propose first randomized construction heuristic, which is inspired actually from a plan right. So we create groups that make sense. We pass this creating dependent routes for every group, and then we calculate time stats for every route possible to see if we can merge routes together. And of course, there will be some cases where you're merging, as in here, you have a slab of this much. This is how much you can delay this first pickup and still arrive to the last slab. And in that, this possible merge will actually give you to do a pickup here, which is more than your slab, so this is feasible. And if you look at this other side, the left side of your screen, you will see that in some cases your slab is actually much larger than what actually the shifting will be the merger, so you can merge them. And this, of course, basically the left and right. So first you calculate your savings, you make sure that you test feasibility in things that make sense, and so on and so forth. But good thing here is that we're able to find a solution for every problem every time. We'll skip the details of that. And then this will give you a solution, and this is one of the heuristics that we tested, but we propose another one, and this one looks to have kind of take use of the information that your iteration of your lower bound gives you. So if the algorithm is telling you a solution, what we propose to do is to have possibility building a solution heuristic which takes the auxiliary network from the lower bound model, but with much coarser target representation, so it's lower and higher and easier to solve, and exploits this information on the group's real time and time restriction, and adding as many nodes as necessary to make the paths that the lower bound will give us. What I'm saying by that is that if your lower bound modeling gives you a solution that goes back in time, you know that you cannot do that, so you create as many nodes as possible to make sure that you arrive to this kind of good time. This auxiliary network is much less crowded than the full extended network, so it's kind of faster, but it's still, as you can imagine, the downside of this is that solving this need as the lower bound model becomes greater or bigger, this one will become even greater or bigger. So it can maybe lead us to not these solutions. But in some cases, it was able to either prove feasibility, which will be a great case if the solution at the end is possible, or if we have or just give us a chance to have a new iteration. And the next thing, which is Down. Oh. But anyway, the next iteration, what we do is that you refine your network. That means two things. Clearing or refining your groups. Making sure that you increase, but not too much. So finding the right compromise there. And increasing the. Any questions until there? So as you see in this high level simple, we have like the movement of the algorithm, right? We start by computing your lower bound. You can actually start by having a first feasible solution with the randomized construction heuristic that we propose. Then you can, as you go, send this information to your graph. Use find and compute. If it's feasible, great. If not, then check feasibility, try to find a feasible solution with the LP. If not, try to find a feasible solution with the newer randomized construction heuristic. If not, try to find a feasible solution or a better upper bound or improve your upper bound with the other heuristic. And then you move by getting higher and higher lower bounds and higher and higher upper bounds. And at some point, actually, when we are able to prove that, this will lead us to a number of loops, and we're able to find a solution. And feasible solution and productivity. So this is the proposition that we have. How we test it, then we go back to this. During this time of working with industry, what it does give us was the time and the space to actually collect data and see what the type of regions that they have. So we have a test bed of, in this case, we're testing with 38 instances that was previously launched to, from real data from Quebec. And as you can see, you can have different type of instances, so it's quite rich in terms of test bed. Networks that are much more dense, especially if you're closer to the Montreal area or urban areas, even around Quebec City can be quite large in terms of number of nodes. Or you can have more sparse networks and also longer distances, so more rural type of settings. What you have here is the number of SCCs that can come in each one of the instances. And then once you have this geographical setting, you can create like actually in almost infinite type of number of instances, because again, each model will depend on the number of commodities that you generate, which at the end will be a decision. What will be the granularity of commodities that I want? Do I want to consider that a new sample is generated in 10 minutes, 15 minutes, 1 hour, 2 hours? That's one thing, and this is the information that you have here on your columns TR, mean, and TR max. TR by transportation request. So in those instances, you start by what the ministry gave us at the beginning, which was like 3 pickups, an average over for 3 centers. So let's say 1 pickup per center, or for some others here, let's say you have 10 centers and 13 pickup, which means that you have a few pickup, a few centers that require more than 1 pickup. That came from the ministry, but you can then explode it against the level of detail that you want. So you can easily go into, in my example of 30 initial pickups, you can actually have 200 commodities that needs to be transported over the world. I think that is the largest one. And then, of course, is the granularity in terms of commodity, but also the granularity in terms of time for your time spent. So you have the number of periods that you can have as minimum as maximum. And the lifespan of the N, and this is another important detail, as this service network defined model that we have here is not used for service network design. It's not for defining the long haul of transportation between the provinces along this traveling, but like a city planning or a regional planning for a daily transportation plan. We have less option in terms of what you can restrict or remove. It's not easy. So usually DDD solves something that goes with a delivery time window of 55 periods or so, and there's some restrictions. You know that from New York to LA, you don't go to, they are not interconnected. In our case, we cannot do that. We need to handle it fully extended, so this can be also quite large. First things that I want to show the first thing that we want to get clear, what's cloudy right and what's not. And then coverage. Is this formulation more strength, more strong than the BRP formulations? It is. So we tested the formulation of mesantianol, which is closest one to the exact conditions that we're having. We have the same number of cups, and then we make sure that everything was comparable, and we solved it in 1 hour with the same objective functions and everything. And as you can see in this graph on your left, you have the blue line, which is the BRP gap percentage for the number of instances from 1 to 38. The red one is the time expanded network. So for the easy instances, the time expanded network can work very well. So the first one, with the number of gaps that the ministry did, we are able to do like super fast optimality. Masanti finds a limit around 26. And here you have the deal right? Then we're starting, their formulation start having problems around instance 26, 29. In our case, we're able to solve optimality. Almost all of them, and in the ones that we're not able to solve optimality directly, we have a very minor gap, except instance 38 where so that worked well. And the reason I think not only that, but the next question is, was it interesting to make this type of detailed model of a decision that they are already telling us that they want really cut? Why do we bother to say less? Well, here you have the number of hookups. Again, red is this method. The first one, of course, explains that the BRP will perform all the hookups that are requested. It's part of the modeling. In our case, our time extended network is able to find less hookups than was expected and that they requested. And of course, as they do less hookups, they're able to have actually better total distance travel. So that also. And next, that's the algorithm. So what we propose, we tested it over the 38 instances in all sorts of different configurations in one MD. We reduced it, and we're showing you here just what makes more sense in terms of detail. So we tested with a delta T, that means granularity, might have expanded 1 minute and 5 minutes. I'm not even going to the 15 minutes here. And the DK, which is the granularity of commodities generation, of 15 minutes, 30 minutes, or 1 hour. So a sample is generated in 15, 30, or 1 hour, 60 minutes. We're able to solve all instances because our algorithm has a heuristic that allows us to provide a solution for every instance. Not only that, we were able to prove optimality for 26 of those 38 instances. The average time to prove optimality over those 26 that we prove optimality is over between 200 and 400 seconds, so 450, 530, depends on the granularity of it. And the average gap of the ones that we're not able to prove optimality is still around 20%, which is, I think, still quite encouraging. As we can imagine, having a higher level of detail in your granularity of time horizons makes the problem harder to solve, but still, I think, quite encouraging. We tested here the reasons why the algorithm stopped, being reasons 1 and 2 that we was able to either prove optimality, feasibility checks in the first after the lower bound, or in the heuristics that we propose. And then, as you can see, it's quite diverse, which means that all the parts of the algorithm are actually contributing to the reason and to the solution of methods. And finally, was important to do all this work and try to make this not only like a reasonable algorithm and working on the commodity groupings. Commodity groupings did add to it, and we show here for the instances that we're able to solve to optimality, the solution of the time of solving the full time spent network versus solving with our algorithm but without commodity grouping, and then the real target, which is the commodity grouping. Then, as you can see, this is not very scale, but it still is able to provide better results. And also, there is some cases when you don't need to go to a very fancy machinery to treat some things, and there are problems with this. And with this, I'm gonna leave you, but I'm not gonna get into details, but we also test things to how's the impact of not having uniform federation, we have different types of demand. In the model, you will even so, I can get into that detail, but the model as we have it now actually allow transfers. In all the instances that we tested was never the case, but we tested and we proposed constraints to avoid this in case it's really, really necessary to avoid it. But the good thing is they're actually kind of not sensitive, I would say, to all that. So kind of give us the chance to those things. And with this, I'm one of those.
All right.
Things that I hope we get to, the key thing or big part of my messages is that this came from a very real case that people are still solving. I was in the tower, I need to have some blood flow this week, and I still saw the up the lab thing, and give us a chance, and then we can discuss a little bit more about that experience. But what I'm trying to give you this is that healthcare and public systems, public health problems are interesting and very challenging. I can give you actually the nice motivation for different types of collaboration. So I work with this in this problem for a while now, and with different type of people, and we have with this, with others that have done linguistics, I've done with them different ways to do it and different approaches. But I think they're quite interesting. For me, more exciting. The formulation we provided become quite interesting. We have we look things at from different angles face up. That was kind of a thing. One of the person that we submitted this, the main comment at the way back was, wait, but you're saying that you're solving a vehicle problem, you're modeling as a service network design. That makes no sense. And of course, I would say that it's not the reviewers' fault. It was our fault that we didn't explain properly why we wanted to do this. Because in the second time we submitted it, actually, this was not highlighted, so I think we explained it better. But my point here is that tackling problems that probably doesn't seem like natural actually can make sense and can be useful. And our algorithm then is able to propose solve to optimize 26 of 30 instances, which is, again, this is the number of periods and the number of commodities that you solve, which is much higher than other DDDs algorithms also. So I think this is an interesting contribution also from the development perspective. And beautiful problems to create fun algorithm, I think, was already a problem. So thank you very much for your time, and I'm open to discuss some more and then how we can introduce this and make this more useful. Thank you.
Thank you very much, Dr. Ana Maria, for a great presentation. So we now open the floor for the audience, and if there are any questions from the audience for the speaker. Yes, Sarah, you can ask.
Small questions. The first one was how many that's with your model actually the results. You said the pages that was asking for 3, and then your model did the pickups. Is that what you said? Or?
In some cases more pickups, in some cases less pickups.
Okay. And then the second question is around did you consider capacity? It was not something that was a challenge.
Very good point. It was not necessary to consider capacity.
Okay.
Because what we're dealing with is they actually put in a small
Box, I'm assuming.
yeah, coolers.
Okay.
When it works, so a small cooler. And the time restriction is so intense that the number of routes, like the routes are not very long at the end. So it's never really an issue. You can put inside their minivans over 200 coolers and still be fine, and we never get to that.
Okay.
So that allows us to remove all this consideration of time we didn't have to. And again, I do think that is moreover, not only the type of commodities, but the time restriction of the commodities makes that the time is the main constraint to add, so there's no need to add fiction constraint just to say that it's a capacity version.
And in order to make it more realistic, was there any other constraints that you would think would be in this case? Like that.
The synchronization aspect and the time restriction aspect of the problem is so complicated that I'm still now getting to get around the grasp of it. And that was where we needed to start. But this is a feminist version. And we're assuming that this, they say 30 minutes and it will take 3 minutes. And not only that, we're assuming that if they tell us 5 hours to the door, they will, because they say 5 hours, because the real time restriction is 6. And they assume that they can do all their operations between lab until final analysis in 1 hour. Big assumption. So I do think that there is extensions that are still necessary and interesting. And I'm actually discussing for a new extension in that sense. And then the question is, what would be the right way to do the certainty? Something more robust, make sure that I cover the basics, something that's an open and thank you.
Okay, so I will then ask one small question. So in your work, you are talking about the vehicles, number of vehicles that are used. So nowadays we talk a lot about, greening efforts and things like that. So are you also looking into, let's say, putting one big truck versus several small vehicles? So is this part of your problem?
No, not at all. So in this case, we are assuming that we will have, so 2 reasons there, and they all come from the practical case. The ministry doesn't have, but the systems use, they don't necessarily are doing this by their own. They actually subcontract the transportation. So there was no question about minimizing the flow to make sure that we respect the number of trucks that we have, number one. And number two, as they are using it like that, they just send this to the PBL and they're including this in their all other transportation plans. However, what you're bringing out, I think makes sense, especially if you're dealing with your own fleet of vehicles. And then the question again, as the time restriction was so intense, this might not be necessarily the case, but when we might think about maybe reducing this a little bit, that of course become interesting. I will probably not the size of the vehicles, but the number and how you locate them, that is something.
Okay. So if there are no other questions, then we would like to thank the speaker once again and acknowledge the students chapter, Montreal students, operations research student chapter in organizing this presentation. Thanks very much and see you in the next course micro event. Have a great day. Thank you.
Thank you.